Ancient engineers achieved the impossible by moving mountains to redirect entire rivers. This is the story of history's lost hydrological geniuses whose forgotten innovations could solve modern water crises. By the end, you will understand how civilizations thrived for centuries using water management secrets we have since forgotten. How did they carve channels through solid rock without modern tools? And why did their most brilliant techniques vanish from history? What does true mastery over nature actually look like? Water was not just a resource, it was the ultimate source of power. The very first empires rose from river valleys not by chance, but by design, built by societies that grasped a fundamental truth. Whoever controlled the water controlled the future. In the Fertile Crescent of Mesopotamia, the life-giving Euphrates and Tigris rivers could either nourish civilization or drown it in destructive floods. In the arid landscapes of the Andes, a single season of drought could erase generations of progress. This constant struggle against nature's whims forged a new kind of social order. Rulers quickly realized that survival required more than just warriors. It demanded a new class of experts, the world's first hydraulic engineers. These were the master planners who studied the subtle pull of gravity, who mapped the seasonal rhythms of rivers, and who learned to read the land itself for signs of stability. Their monumental task was to build systems that could capture floodwaters, store them through long dry periods, and distribute life across vast territories to feed burgeoning cities. This deep, accumulated knowledge of moving water became the empire's most guarded secret, the bedrock of its authority. It was this foundation of centuries of observation and innovation that would one day give engineers the audacity to look at a mountain and decide to move it. But the Persian solution was not to fight the desert, but to outsmart it. Deep beneath the scorching sands, a hidden network of veins began to pulse with life. These were the Qanats, a masterpiece of ancient engineering that turned the very concept of water delivery on its head. Instead of relying on unpredictable surface rivers, Persian engineers learned to tap into secret reservoirs, the vast, hidden aquifers trapped deep within the mountain rock. The concept was brilliantly simple in theory, yet staggeringly complex in execution. They would begin by sinking a mother well deep into the foothills, all the way down until it struck this submerged water table. Then came the true marvel. Teams of skilled diggers, known as muqanis, would begin carving a gently sloping tunnel backward from their settlement, often dozens of miles away, meticulously meeting the mother well deep underground. This was not random digging. It was a precise surgical operation guided by generations of accumulated knowledge. The slope was everything. A mere fraction of a degree too steep, and the water would rush through, eroding the tunnel walls and carrying destructive silt. A fraction too shallow, and the flow would stagnate, allowing sediment to choke the precious channel. How did they achieve such impossible precision over such vast distances with only ropes, plumb bobs, and simple sighting tools? They used the stars for alignment and developed ingenious leveling instruments to maintain the perfect gravity-fed gradient. But building the tunnel was only half the battle. These workers toiled in complete darkness with the constant, terrifying threat of cave-ins and poisonous gases. They needed air to breathe, so at regular intervals, they would dig vertical shafts straight up to the surface. These shafts, which from above look like a line of craters marching across the desert, served a dual purpose. They provided vital ventilation for the diggers below, and they also became access points for the centuries of maintenance the Qanat would require. The result was a system that delivered cool, clean water directly to the heart of cities and fields, completely protected from the evaporating heat of the sun. It transformed barren landscapes into lush gardens and thriving metropolises, creating pockets of paradise where none should have existed. This was not brute force. It was a profound collaboration with the laws of nature, a quiet, underground revolution that would quench the thirst of empires for 1,000 years. These underground rivers did not appear by chance. They were the result of a deep and intimate understanding of the mountains themselves. Ancient engineers saw these towering landforms not as solid, impenetrable barriers, but as living, breathing water towers. They possessed a sophisticated grasp of mountain hydrology, recognizing that every peak was a giant sponge, collecting rain and snowmelt in its porous heart. They learned to read the landscape like a map, identifying subtle clues that pointed to hidden water, a particular type of vegetation clinging to a rocky slope, a specific color or fracture pattern in the rock face. Even the morning dew patterns could reveal the presence of a submerged aquifer. They understood that different rock layers acted as natural filters. Impermeable stone, like granite, would force water to flow over its surface, while porous sandstone could absorb and hold vast quantities, releasing it slowly over time like a stone reservoir. This knowledge was not abstract, it was intensely practical. They developed methods to estimate the total volume of water a mountain could provide by studying the size of its catchment area, the basin where all precipitation collected, and correlating it with generations of rainfall records. This allowed them to predict with startling accuracy how much water would be available during the dry season, or how the system would fare during a prolonged drought. Their entire approach was systematic, a science built on centuries of observation. This hydrological wisdom, this ability to see the invisible water within the stone, was the true foundation upon which empires built their thirst-quenching marvels. While Persian engineers worked in hidden tunnels, Roman engineers built their mastery in plain sight, transforming the very skyline with monumental stone rivers. Their aqueducts were not just functional structures, they were bold declarations of power and precision, defying gravity and geography to conquer distance. The secret to their success was a mathematical obsession with the perfect gradient. Roman engineers developed formulas to calculate a slope so subtle it seems impossible, a drop of just a few feet for every mile of channel. This gentle incline was the heart of the entire system. Too steep, and the water would rush forward with destructive force, eroding the delicate lead or stone channels. Too flat, and the flow would stagnate, allowing sediment to build up and block the vital current. Achieving this perfect balance required a level of surveying accuracy that would challenge even modern engineers. Their primary tool for this was the chorobates, a massive wooden bench nearly 20 feet long. The surveyor would fill a central groove with water, using the still surface as a reference line to ensure the channel's path maintained its relentless, gentle descent across hills and valleys. For aligning straight paths over vast distances, they used the groma, a simple but effective instrument that used suspended weights to sight perfect right angles and straight lines across the landscape. But their genius did not stop at measurement. When the path encountered a deep valley, Roman engineers did not divert the water down and back up. Instead, they built soaring bridges of stone arches. The arch was their masterstroke. This shape distributed the immense weight of the water-filled channel above, down, and outwards through the pillars, allowing the aqueduct to maintain its crucial elevation across any obstacle. And to build these colossal structures in marshes or across rivers, they developed a revolutionary material, a concrete that could actually harden underwater. This unique mix of lime, volcanic ash, and rubble created a chemical reaction, forming a crystalline structure that bonded with the stone, making their aqueducts not just grand but virtually eternal. This entire system, from mountain spring to city center, was a testament to systematic planning. The water that flowed into Rome powered a hydraulic civilization. It supplied vast public baths that were centers of social life, countless fountains that cooled the air, and a complex sewer system that flushed waste from the streets, contributing to public health on an unprecedented scale. The aqueduct was the lifeblood of the city, a constant flowing reminder that Roman order could tame nature itself. Far from the arid Persian plains and Roman lowlands, another civilization faced a completely different hydrological challenge. High in the punishing peaks of the Andes, the Inca Empire confronted a vertical world. Here, fertile soil was a precious strip clinging to impossible slopes, and water either cascaded down in torrential floods or vanished into thin, high-altitude air. To survive, they did not tunnel through mountains or bridge valleys. Instead, they re-sculpted the mountains themselves, creating a breathtaking landscape of cascading terraces that turned sheer cliffs into fertile farmlands. These were not simple stone walls. Each terrace was a complex, multi-layered structure, a feat of engineering designed to defy gravity and time. At its base, a foundation of crushed rock provided essential drainage, preventing water from pooling and destabilizing the structure. Above this, layers of clay, sand, and rich topsoil were carefully laid down, creating a deep, stable bed for crops. The retaining walls themselves were masterpieces of stonework, built from blocks so precisely cut and interlocked that they needed no mortar. This intentional design was their secret weapon against the constant threat of earthquakes. During a tremor, a rigid mortar-bound wall would crack and crumble. But an Inca terrace wall would simply shift and settle, the stones dancing together before locking back into place, a flexible system that could withstand the Earth's violent movements. Yet, building these stone staircases to the sky was only half the solution. The true genius lay in making them live. Water, the lifeblood of this system, presented its own unique puzzle at such dizzying heights. Here, the thin air and lower atmospheric pressure changed how water behaved, making it evaporate more quickly and freeze more readily. Inca engineers developed an intricate network of stone canals and aqueducts that snaked along the mountainsides, capturing water from distant glacial streams and mountain springs. They calculated the gradients of these canals with the same precision as the Romans, but for a different reason. Their goal was not just to maintain flow, but to slow it down, to prevent the water from gaining destructive speed as it traveled down the steep slopes. They built gentle curves and settling basins into the canals to reduce erosion and trap sediment. From these main arteries, a capillary-like system of smaller channels then distributed the water horizontally across thousands of individual terraces, ensuring every single plot received its share of the mountain's bounty. This harmonious fusion of terracing and irrigation created a self-regulating agricultural machine. The terraces prevented the very erosion that would have choked the canals with silt, while the canals delivered the water that allowed the terraces to flourish. It was a closed, sustainable loop that transformed the Andes into a vertical breadbasket, capable of supporting vast cities like Machu Picchu in locations that would otherwise have been completely uninhabitable. They did not conquer the mountain, they learned to dance with it step by engineered step. Precision was not born from lasers and satellites, but from water, shadow, and string. To redirect a mountain's flow, ancient engineers first had to conquer the invisible world of measurement, translating the chaotic landscape into lines and angles on a map. Their most fundamental tool was also the most humble, a simple trench filled with water. By digging a long, narrow channel and filling it with water, they created a perfect, unerring horizontal plane, a reference line that gravity itself guaranteed. They would then use this still water surface to mark heights on stakes at intervals, effectively drawing the land's first contour lines directly onto the earth. This method allowed them to visualize the gentle slopes necessary for their canals and aqueducts across miles of uneven terrain. For aligning these long, straight paths, they turned to the sky. A pair of simple sighting poles topped with flags or plumb bobs allowed a surveyor to line up a distant target with his eye. His assistant would then move from point to point, always staying in that precise line of sight, effectively painting an invisible straight line across hills and valleys. But what happened when they needed to see over a hill or maintain alignment through a forest? This is where the shadow stick or gnomon came into play. By tracking the movement of a vertical rod's shadow throughout the day, they could establish true north-south and east-west axes with astonishing accuracy, using the sun as their fixed celestial guide. For the most complex tasks, like plotting a course through a mountain pass, they employed the dioptra, a revolutionary instrument that functioned as an early theodolite. This device featured a circular metal plate marked in degrees and a sighting tube that could pivot horizontally and vertically. By peering through the tube and aligning it with a distant marker, an engineer could measure angles of elevation and bearing, calculating the precise rise and fall of the land between 2 points. Distances themselves were measured with remarkable ingenuity. They used long, specially treated cords that resisted stretching, knotted at precise intervals. Teams would literally walk the course, unspooling this graded cord to measure the land. On rougher ground, they might use a large, calibrated wooden wheel, counting its revolutions to determine distance traveled. All of this raw data, these angles and distances, then had to be processed. They developed sophisticated mathematical formulas to account for the Earth's curvature over long distances and to calculate the volume of earth that needed to be moved for a cutting or an embankment. This entire process, from the water-filled trench to the final calculations, was a symphony of simple tools guided by profound understanding. It was this patient, meticulous art of seeing the land that allowed them to draw a line on a map and then go out into the world and move a mountain to match it. The true test of an engineer's vision is not how a structure begins, but how it endures. These monumental water systems, carved through mountains and stretched across valleys, had to survive for generations, and their longevity came down to a single critical choice: the very stones and mortars that held them together. Ancient engineers were master material scientists, possessing an intimate knowledge of the land's raw ingredients. They did not simply use the nearest rock. They selected stones based on a deep understanding of their properties, seeking out specific types of granite for its crushing strength in an aqueduct's foundation, or a particular sandstone for its ability to filter water while resisting erosion. Quarries were often miles, sometimes hundreds of miles, from the construction site, and the immense effort of transporting these perfect blocks was a calculated investment in permanence. But stone alone was not enough. The gaps between these massive blocks were the system's vulnerable points, and here, ancient chemistry took over. Across the world, engineers developed custom mortars, each a unique recipe refined for its local environment. Roman engineers created a revolutionary substance by mixing lime with a specific type of volcanic ash found near the city of Pozzuoli. When this mixture combined with water, it triggered a chemical reaction that formed a crystalline network, a concrete that did not merely resist water, but actually grew stronger and more solid when submerged. This was the secret behind their enduring harbor walls and aqueduct piers. In China, engineers faced a different enemy: the brutal cycle of freezing and thawing. Their solution was a lime-based mortar enhanced with sticky rice. The organic compounds from the rice created a more plastic, flexible binder that could expand and contract with the temperature swings without cracking, ensuring that canals and levees held firm through harsh winters. Meanwhile, in the arid Americas, engineers tapped into natural petroleum seeps, using thick bitumen to create completely waterproof linings for reservoirs and canals. They also experimented with plant-based sealants, boiling certain barks and saps to produce a tar-like substance that would repel water for decades. This profound, localized knowledge of materials meant that every water system was perfectly adapted to its specific climatic challenges. The result was infrastructure built not for a lifetime but for an age. Some of these ancient channels and reservoirs are still in use today, a quiet testament to the forgotten science of stones that breathe and mortars that heal, silently carrying the wisdom of the past into the present. 2,000 years ago, a Chinese governor faced an impossible task. The Min River was a violent, unpredictable force, flooding with devastating power one season and shrinking to a trickle the next, leaving the fertile Sichuan basin in a cycle of famine and despair. The governor, Lai Bing, was ordered to tame it, but his solution defied conventional wisdom. Instead of building a massive dam to block the river's might, he decided to work with its energy, not against it. His creation, the Dujiangyan irrigation system, would become one of history's most enduring masterpieces of hydrological engineering. The core of Lai Bing's strategy was a man-made island, a long, wedge-shaped levee known as the fish mouth. Constructed from enormous bamboo cages filled with stones, this structure was positioned directly in the center of the river's flow. Its brilliant shape was designed to exploit the water's own behavior. During the low water season, the fish mouth naturally diverted about 60% of the river's flow into an inner channel, while 40% continued down the main riverbed, ensuring both irrigation and navigation could continue. But when the summer floods came, this ratio would magically reverse. The rising waters, pushed by their own immense power, would overtop the fish mouth, sending the majority of the destructive floodwaters and their heavy silt load back into the main river, while the inner channel received a safer, cleaner volume. This was a self-regulating diversion system, an automatic water switch built from stone and bamboo. Yet, to get this water to the arid plains, Lai Bing's engineers faced a sheer mountain of solid rock. The solution was as daring as it was dangerous. They would carve a channel right through it. Without dynamite or power tools, they turned to the elements themselves. Workers built large fires directly against the cliff face, heating the stone until it was red-hot and brittle. Then, they quickly doused the superheated rock with cold water. The violent thermal shock caused the granite to fracture and crumble, allowing teams with simple chisels to break it apart piece by piece. This method of controlled fire and water created the Bow Pass, a 20-meter-wide channel that still carries water today. The final component of this ancient marvel was perhaps its most clever. The system included a spillway called the Flying Sand, a low weir that connected the inner channel back to the main river. This feature was engineered to solve the silent killer of all water systems, silt buildup. As water flowed through the inner channel, the slower-moving water along the bottom would naturally deposit its sediment. The Flying Sand weir was calibrated to a precise height. When the water level rose during a flood, it would overtop this weir, and the resulting vortex action would actively suck the accumulated silt up from the channel bottom and flush it back into the main river. This was an automatic, energy-free dredging machine, ensuring the channels never clogged and maintained their perfect depth for centuries. The Dujiangyan system transformed a catastrophe zone into the land of abundance, an agricultural powerhouse that supported millions. It stands not as a monument of conquest, but as a lesson in intelligent harmony, a 2,000-year-old conversation between human ingenuity and the power of a river. Yet the mountains did not yield easily to their will. Carving a path through solid rock was a brutal, painstaking process, a battle of wits and endurance fought with the most elemental of tools. Ancient engineers became masters of geology, developing a specialized toolkit of rock-breaking methods tailored to the stone they faced. For the hardest granites and basalts, fire setting was their most powerful technique. Workers would build roaring fires directly against the rock face, heating it for hours until the stone glowed. Then crews would rush in, dousing the superheated surface with water or sometimes with vinegar. The sudden, violent contraction caused by the rapid cooling created a web of microfractures, weakening the stone's internal structure and making it possible for workers with bronze or iron picks to pry away large chunks. This method of thermal shock was dangerous and required precise control, but it allowed them to fracture stone that would have defied their chisels alone. In softer sedimentary rocks like sandstone or limestone, the work was different but no less demanding. Here, teams wielding heavy stone mauls and metal-tipped pickaxes could carve directly into the mountain, cutting channels and tunnels through sheer, repetitive force. The rhythmic pounding of hammers against stone must have echoed for months, even years, through the valleys as they slowly, inexorably, advanced their cuts. For the most stubborn limestone formations, some cultures discovered a chemical solution. They found that applying weak acids like fermented vinegar or soured wine could slowly dissolve the calcite binding the rock together. By repeatedly applying these acidic solutions to a targeted seam, they could soften and disintegrate the stone over time, essentially eating their way through the mountain ridge. But this was not mere brute force excavation. Every cut, every fracture was guided by a profound understanding of the rock's anatomy. These engineers knew how to read the natural fault lines and cleavage planes within the stone. They would probe for weaknesses, following the subtle grain of the mountain to determine the most efficient and stable path for their channel. A misjudgment could mean a catastrophic collapse, burying years of work in an instant. They were not just diggers, they were underground architects, ensuring that the roof of their tunnel and the walls of their cutting would stand for centuries. The sheer scale of their perseverance is almost unimaginable. Some of these rock-cut channels extend for miles through the very heart of a mountain range, a testament to generations of laborers who dedicated their lives to moving a river, one hammer strike at a time. The true genius of these water systems was not just in their construction, but in the invisible calculations that made them work. Before a single stone was laid, ancient engineers had to solve a complex mathematical puzzle, predicting exactly how much water would flow and where it would go. Their survival depended on this precision. They developed an intuitive grasp of hydraulic principles we now formalize as equations, understanding that the amount of water a channel could carry, its discharge rate, was a product of its cross-sectional area and the speed of the current. A wider, deeper channel with a steeper slope would naturally carry more water, but only up to a point. They learned through observation and recorded data that friction from the channel walls and bed would slow the flow, a loss they had to account for over long distances. This was not guesswork. They created standardized formulas passed down through generations of master builders that linked channel dimensions to expected output. In Babylon, this mathematical prowess was applied with brilliant fairness. Engineers used geometric progressions to design their vast canal networks. If a primary canal had a certain capacity, the secondary channels branching from it would be sized according to a precise geometric ratio. Then the tertiary channels from those would be reduced by the same ratio. This systematic scaling ensured that water pressure and volume were distributed equitably to farms across the entire region, preventing disputes and guaranteeing that the most distant fields received their fair share. This was mathematics in service of social order. Meanwhile, Greek and Roman surveyors faced the problem of maintaining a consistent gradient across wildly uneven ground. Their solution was an elegant application of geometry. Using the principle of similar triangles, they could transfer a perfect slope over any obstacle. If they needed to run a channel from a mountain spring down to a distant city, they would set up a series of sighting poles. By ensuring that the height of each pole formed an identical triangle with the one before it, they could guarantee the water's gentle, unerring descent across hills, through valleys, and over plains. This mathematical foundation transformed water from a chaotic force of nature into a predictable, manageable resource. An engineer could stand at a mountain source and, with a set of calculations, know with certainty that a specific volume of water would arrive at a city's gates days later. This reliability, born from numbers scratched on clay tablets and simple geometric rules, was the silent, beating heart of every empire. It makes you wonder, what other profound truths did they discover that were simply lost to time, their formulas fading long before their stone channels finally fell silent? But the ultimate test of hydrological genius unfolded in one of the most unforgiving places on Earth. In the high desert of southern Peru, where rain might not fall for years, the Nazca civilization faced extinction daily. Their survival and the creation of their mysterious desert drawings hinged on a single, audacious invention, the Puquios. These were not canals or terraces, but something far more clever, spiral stone wells that reached deep into the desert's hidden veins. The design was a masterpiece of form and function. From the surface, a Puquio appeared as a circular stone-lined shaft plunging straight down into the earth. But as it descended, it began to curve, transforming into a vast, open-air corkscrew that spiraled gracefully into the ground. This helical shape was not for artistic flair. It served a critical dual purpose. First, the gentle, winding ramp provided stable access for generations of maintenance workers who could descend to clear blockages and repair the stonework, ensuring the system's survival for centuries. Second, and more brilliantly, the spiral acted as a natural cooling tower. As wind swept across the desert floor, it would funnel down into the open shaft, creating a constant, gentle downdraft. This moving air cooled the stone walls and the water within, dramatically reducing loss to the relentless desert sun. At the bottom of this stone vortex, the true magic began. Horizontal tunnels, known as filtration galleries, branched out like the roots of a tree. These low, stone-lined passages were carefully engineered to intersect with the subsurface water table. They did not simply collect water, they guided it. The galleries were built with a slight upward slope away from the main shaft. This counterintuitive design forced the water to follow the path of least resistance, naturally flowing back toward the central collection point, all powered by gravity. The Nazca engineers possessed a deep, almost mystical understanding of the desert's hidden hydrology. They knew which dry riverbeds or quebradas acted as natural infiltration zones during the rare mountain rains. They could pinpoint where the porous subsoil would channel this precious water into deep, underground reservoirs. Their entire network of Puquios was strategically placed along these invisible groundwater pathways, tapping into multiple sources to create a resilient, interconnected web. This deep knowledge of seasonal recharge allowed them to design a system that provided a consistent, reliable water supply year-round, even during decades of drought. The result was the creation of life-giving microclimates in the midst of barren sand. The cool, humid air rising from the Puquios allowed for the cultivation of small, fertile oases where crops could flourish. This steady water supply did more than just quench thirst and feed the people. It provided the logistical foundation for one of history's greatest enigmas. The same society that built these spiral wells also created the vast Nazca lines. With their survival secured by the Puquios, they could dedicate time and immense communal effort to etching giant figures into the desert pavement. The water that flowed from these stone spirals likely sustained the teams of artists who created these geoglyphs, turning a desperate struggle for existence into a canvas for profound cultural expression. The Puquios were not just wells, they were the beating heart of a civilization that learned to drink from the stone itself. A mountain channel is only as reliable as the hands that tend to it. These colossal waterworks, carved through stone and earth, demanded more than just brilliant construction. They required a promise of perpetual care. Ancient societies developed intricate maintenance regimes, a rhythmic cycle of cleaning and repair that turned engineering marvels into living, breathing systems. This ongoing labor was a sophisticated science in itself, perfectly synchronized with the seasons. During the dry season, when water levels dropped to their lowest, armies of maintenance crews would descend into the empty channels. Their primary task was sediment removal, the relentless battle against the silt and debris that could slowly choke the life from a waterway. Using shovels, baskets, and drag buckets, they would scrape and haul the accumulated muck, ensuring the channel's capacity was fully restored before the next flood. This was dirty, dangerous work, but it was meticulously scheduled. Engineers kept detailed records of seasonal flow patterns, knowing exactly when a brief window of low water would grant them access to the system's arteries. To make this work possible, they designed the infrastructure with foresight. Along the length of an aqueduct or a Qanat, they built regular access points and inspection chambers. These were not mere holes in the ground, but carefully constructed stone rooms that allowed engineers to descend and monitor the structural integrity from within. They could check for cracks, assess the condition of the waterproof lining, and test the water's clarity and flow rate without disrupting the entire system. This was preventative medicine for their stone and concrete patients. The operation of these vast networks was a masterclass in logistics and coordination. Water was not simply released, it was conducted. A complex system of sluice gates and weirs, managed by a dedicated class of water masters, acted as the valves and switches of the entire network. These operators followed strict schedules, opening and closing gates to direct water to different districts based on a pre-arranged roster. During planting season, the gates would swing open to flood the agricultural terraces. As harvest approached, the flow would be redirected to urban centers to supply public fountains and baths. This was a delicate dance of supply and demand, managed with the precision of a modern utility. The most vital component of this entire system, however, was not stone or water, but knowledge. The subtle behaviors of a water system, the quiet signs of an impending collapse, or the trick to repairing a specific type of mortar, could not be written down in a simple manual. This wisdom was passed from master to apprentice through generations. A young engineer would spend years alongside a veteran, learning to interpret the sound of water flowing through a tunnel, to recognize the faint discoloration on a wall that signaled internal erosion, and to understand the precise consistency of the lime-mortar mix that worked best in their local climate. This living chain of expertise, this slow and careful transfer of intuition, was the ultimate safeguard. It was this profound, long-term commitment to upkeep that allowed some of these systems to function for over 2,000 years. They were not static monuments, but evolving partnerships between human society and the landscape, a testament to the understanding that true mastery over nature is not a single victory, but a promise renewed with every changing season. These ancient systems were not just built for the weather of their time, but for the climate of the ages. They were designed from the ground up to be resilient, to bend without breaking under the pressure of decades-long droughts and biblical floods. This was not luck, but a profound anticipation of nature's unpredictable moods. The first line of defense was diversity. Engineers rarely relied on a single river or spring. Instead, they tapped into a portfolio of water sources, each with its own unique behavior. A system might draw from a high mountain glacier stream, which provided a steady, cold flow throughout the summer melt, while also connecting to a series of foothill springs fed by deep aquifers that recharged slowly over years. These groundwater sources would remain robust even when the surface streams ran dry during a drought. By weaving these different sources together, they created a hybrid system that could compensate for the failure of any one part. If the glacier-fed river shrank, the spring-fed canals could take over, ensuring the civilization never faced a total water collapse. This multi-source strategy was their insurance policy against a fickle climate. But diversifying supply was only half the battle. They also mastered the art of banking water for a non-rainy day. Their storage reservoirs were not just simple ponds, they were precisely sized for the long haul. Engineers calculated the catchment area of a region, studied centuries of rainfall records passed down through oral tradition or early writings, and then designed vast, lined basins to capture every possible drop during the rare wet seasons. The reservoirs of Petra, carved directly into the rose-red cliffs, or the massive tanks of ancient India, were engineered to hold enough water to sustain entire cities through multiple years of drought. The sizing was a deliberate calculation of risk, a buffer against the certainty of future scarcity, and when the rains did come, they often arrived with violent force. Ancient engineers knew that a system must be able to safely release this destructive energy. They designed elaborate spillways and overflow channels that acted as pressure relief valves. Instead of allowing a flood to overtop and shatter a main canal wall, these secondary pathways would activate, diverting the excess water away from critical infrastructure and into designated floodplains or secondary storage areas. The primary structure remained intact, ready to function again the moment the flood subsided. In regions shaken by earthquakes, their designs incorporated a flexibility that seems almost modern. They understood that a rigid structure would be shaken apart. In Peru, Inca masons built their canal walls with interlocking stones that could shift and settle during a tremor before locking back into place. Roman aqueducts sometimes featured lead joints in their water channels, a material that could absorb and distribute seismic shock without fracturing the surrounding stone. They even designed sections of canals with curved alignments to better dissipate the energy of a seismic wave. This was shock absorption engineered in stone. The final layer of climate intelligence was active management. Many systems featured adjustable weirs and wooden gates that could be raised or lowered by water masters. These were the ancient equivalent of a control room. If seasonal predictions, based on generations of observing animal behavior, plant cycles, and star positions, suggested a coming drought, the gates could be adjusted to conserve water in the upper reservoirs. If a heavy flood season was expected, the gates could be opened preemptively to create more storage capacity. This was not a static monument, but a dynamic, responsive machine. The enduring lesson is not just about engineering strength, but about designing with humility for an unpredictable world. These civilizations built for a future they would never see, creating systems that could whisper to the mountains and negotiate with the floods for 1,000 years. Some of the world's most profound water solutions were not built up but carved down directly into the heart of the earth. In the arid plains of India, where the sun could bake the land for months on end, engineers responded to the climate with breathtaking inversion, creating not towers, but subterranean cathedrals of water known as stepwells. These were far more than simple holes in the ground. They were magnificent multi-story structures carved deep into the aquifer, with intricate staircases cascading down from the surface to meet the fluctuating water table. Their brilliant design was a direct answer to the region's extreme seasonality. During the scorching dry months, the water level would gradually recede, sometimes dropping 100 feet or more. But the Stepwell remained accessible. Its vast, stepped corridors allowed people to simply walk down to the water, step by step, ensuring a reliable supply even at the very end of a long drought. Simultaneously, by placing the entire reservoir deep underground, engineers cleverly shielded the precious water from the evaporating heat of the sun, a passive cooling system of immense scale. The Stepwell was a masterwork of water harvesting. Its wide, open mouth at the surface was designed as a massive catchment basin. During the intense monsoon rains, a network of subtle channels carved into the surrounding landscape would guide the torrential runoff into the well. But this incoming water was often muddy and contaminated. The solution was built into the descent. As the water flowed down the steps and through various chambers, it would pass through layers of naturally filtering sand and crushed stone. These layers acted as a sieve, trapping sediment and impurities, delivering cleaner, clearer water to the reservoir at the bottom. This was a public water treatment plant powered entirely by gravity. Yet, the true genius of the Stepwells lies in their fusion of utility and soul. They were never just utilitarian reservoirs. Architects adorned them with the grandeur of temple architecture, carving ornate columns, sculpted deities, and prayer niches into the very walls that held back the earth. As you descended, you left the harsh, blinding world above and entered a realm of cool, quiet tranquility. The deep stone construction and the presence of the water itself created a natural microclimate, often 10 or 15 degrees cooler than the surface. This made the Stepwell a vital social hub, a community living room where people, especially women who traditionally collected water, could gather, socialize, and find respite from the heat. They became centers for festivals, meditation, and pilgrimage. This was engineering that understood human nature. It solved the physical problem of water scarcity while also nurturing the community's cultural and spiritual needs, creating an oasis for the body and the soul in one profound underground space. The sheer scale of these projects demanded a new kind of human machinery. Before a single stone could be moved, engineers had to solve the ultimate logistical puzzle: how to feed, house, and direct an army of workers for generations. Their solution was a masterpiece of social organization, perfectly synchronized with the rhythms of nature. They planned construction around the agricultural calendar, harnessing the power of idle hands. During the planting and harvest seasons, the workforce remained in the fields, but in the long, dormant off-season, these same farmers would transform into a massive labor corps, providing the muscle for monumental public works. This cyclical system kept food production stable while advancing projects that benefited the entire society, a virtuous cycle of shared effort and shared reward. This vast workforce was not an undifferentiated mass. It operated with the precision of a modern assembly line, broken down into highly specialized teams, each with its own distinct skills and tools. Surveyors, the elite strategists of the operation, would first map the route using their sighting poles and water levels. They were followed by the rock breakers, the toughest of the crews, who used fire setting and heavy mauls to fracture the mountain spine. Then came the masons, true artists in stone, who shaped the rough-hewn channels into smooth, durable waterways. Finally, water testers would conduct the final quality checks, releasing measured flows to ensure the gradient was perfect and there were no hidden leaks. This division of labor ensured that every stage of the construction was handled by experts, maximizing both efficiency and the quality of the final structure. Managing such complexity required a robust administrative backbone. Project engineers developed sophisticated tracking systems using clay tokens, knotted cords, and early forms of ledger keeping to monitor progress. These records detailed the distribution of tools, the allocation of daily food rations, and the completion of specific sections of the work. This was not mere bookkeeping. It was the central nervous system of the project, allowing managers to identify bottlenecks and redeploy resources where they were most needed. A hierarchical chain of command ensured orders flowed smoothly from the chief engineer down to the newest laborer. Experienced engineers provided the overall vision, while foremen, often promoted from the ranks of the most skilled workers, translated that vision into daily tasks for their crews, maintaining discipline and morale on the front lines of construction. The human element was paramount. In remote mountain passes or deep within desert digs, you could not expect thousands of workers to simply fend for themselves. The ancient world's great construction sites were essentially mobile cities, with managers organizing the continuous supply of food, fresh water, and shelter. They established temporary settlements with barracks, kitchens, and medical stations to treat injuries and prevent the outbreak of disease. This investment in worker welfare was not born of charity, but of cold, hard calculation. A healthy, well-fed workforce was a productive one, and retaining skilled laborers over many years was far more efficient than constantly training new replacements. This holistic approach to project management, which considered every factor from seasonal cycles to daily meals, reveals an administrative genius that rivaled their engineering prowess. It makes you wonder, what could our modern mega projects learn from this ancient, deeply human-centered approach to moving mountains? The stone channels and spiral wells were more than just engineering, they were acts of devotion. In societies where water was the difference between life and death, its control was not merely a technical challenge, but a sacred dialogue with the gods. The very first cut into a mountainside, the placement of a foundation stone in a canal, these acts were often preceded by solemn ceremonies. Priests and engineers would stand side by side, offering sacrifices and chanting prayers, not just for the project's success, but for the safety of the workers who risked their lives in the treacherous depths. They were pleading with the mountain spirits for permission to pass, or appeasing a river deity whose flow they were about to redirect. This spiritual framing transformed backbreaking labor into a communal holy mission, a shared endeavor that bound the entire society together. The engineers themselves held a unique, almost mystical status. They were not just builders, they were the interpreters of the water's will. In the Andes, the engineers who designed the mountain terraces were believed to understand the language of the Apus, the powerful mountain gods who controlled the rain and springs. In ancient Mesopotamia, the canal builders were seen as servants of Inca, the god of wisdom and fresh water, and their technical knowledge was considered a divine gift. This respect granted them immense authority and ensured that their complex instructions, which might take generations to complete, were followed without question. The infrastructure itself became a landscape of worship. A simple public fountain was rarely just a source of water. It was often an ornate shrine, with water spouting from the mouth of a stone lion or flowing past carved deities. The magnificent stepwells of India are the ultimate expression of this fusion, their breathtaking architecture descending into the earth like a pilgrimage into the underworld. People did not just go there to collect water, they went to pray, to meditate in the cool, quiet depths, and to honor the goddesses associated with life-giving springs. This spiritual connection created a powerful, self-reinforcing cycle of preservation. a community is far less likely to neglect or vandalize a water source they believe is inhabited by a divine presence. The careful maintenance of a Qanat or a terrace system became a religious duty, a way to honor the ancestors who built it and the gods who sustained it. This cultural framework embedded the need for upkeep into the very identity of the people, ensuring that knowledge was passed from parent to child not as a mere chore but as a sacred trust. The longevity of these systems, some lasting 2 millennia, stands as a testament to this powerful union. It was a partnership of stone and spirit, where faith provided the enduring will and engineering provided the enduring way. Granite blocks weighing tons locked together without a single drop of mortar, a stone puzzle defying gravity for nearly 2,000 years. This is the Aqueduct of Segovia, a Roman masterpiece where engineering precision meets sheer audacity. Its journey begins over 9 miles away in the Sierra de Guadarrama Mountains, where frigid springs feed the channel. From that distant source to the heart of the city, the water descends with an almost imperceptible slope, a gradient so perfectly calculated that it loses only about 1 foot of elevation for every mile it travels. This gentle, relentless pull of gravity is the silent engine of the entire system, a mathematical certainty carved in stone, but the aqueduct's true drama unfolds as it enters Segovia itself. Here, the engineers confronted a steep urban valley. Instead of diverting the channel on a long, costly detour, they made a bold choice. They drove the aqueduct straight through the city center, lifting it high into the air on a breathtaking 2-tiered gallery of arches. The lower arches are broad and powerful, shouldering the immense weight, while the upper tier is more slender and elegant, carrying the water channel itself across the skyline. This was not just a bridge for water, it was a monumental gateway announcing Roman order and ingenuity to everyone below. Yet this soaring structure was filled with quiet, practical intelligence. Before the water even reached the city, it passed through large, rectangular sedimentation tanks. Here, the flow would slow down, allowing sand, silt, and other debris to settle to the bottom. This simple but effective process meant that cleaner, clearer water entered the distribution network, protecting the complex system of lead and ceramic pipes from blockages and erosion. And to protect those very pipes from the destructive force of water pressure, especially where the channel plunged downward, the Romans incorporated clever pressure reduction features. They would sometimes use stepped cascades or wider basins that allowed the water to calm and slow, dissipating its energy before it entered the fragile urban plumbing. This careful management of force prevented bursts and leaks for centuries. The proof of its resilience is written in its long history. It has endured violent earthquakes that toppled lesser buildings, witnessed wars and sieges, and faced centuries of sun, wind, and frost. Remarkably, it continued to carry water for the city until just recently, a functioning piece of ancient infrastructure in the modern world. The Aqueduct of Segovia stands as the ultimate testament to a core Roman principle, that true engineering genius lies in balancing colossal scale with an unwavering focus on the smallest practical details, creating a legacy that flows as steadily as the mountain water it was built to carry. The flow of water mirrored the flow of ideas across the ancient world. Engineering genius was not born in isolation, but traveled along the same dusty trade routes that carried silk and spices, creating a hidden current of shared knowledge that transcended empires. When Persian engineers perfected the Qanat, that technology did not remain a secret for long. It flowed westward into Egypt and the Roman world, and astonishingly, eastward along the Silk Road all the way to the oasis towns of Western China. This was not theft, but a slow, deliberate osmosis of technique. Diplomats and merchants, seeing these incredible systems functioning in foreign lands, carried the concepts home in their minds, sparking new projects thousands of miles from the original source. The Romans were masters of this adaptive engineering. Their monumental aqueducts were not a purely Roman invention. They absorbed and refined the tunnel digging expertise of the Etruscans, who had carved elaborate drainage channels through the bedrock of their own cities. For the mathematical precision needed to calculate their legendary gradients, Roman surveyors turned to the geometric principles developed by Greek thinkers. They took these disparate pieces of knowledge and fused them into something greater, a standardized system of water management that could be replicated across their vast empire, from the hills of Britain to the deserts of North Africa. This cross-pollination of ideas reached its zenith during the Islamic Golden Age. In great centers of learning like Baghdad and Cordoba, scholars gathered texts from across the known world, translating Roman engineering manuals, Persian hydrological studies, and Indian mathematical treatises into Arabic. Engineers of this era did not simply copy these works, they synthesized them. They combined the Roman understanding of arches and concrete with the Persian mastery of groundwater and the Indian innovations in reservoir design, adding their own breakthroughs in water-raising devices and automated control systems. The result was a new, unified science of water that drew from the best of every civilization that had come before. But how did this intricate knowledge, often an empire's most valuable secret, actually transfer from one culture to another? Sometimes it moved with the engineers themselves, captured in war or lured to new projects with promises of wealth and prestige. A skilled Muqani from Persia, with a lifetime of knowledge on maintaining Qanat gradients, could find his expertise in high demand in a newly conquered Roman province. At other times, the transfer was peaceful and scholarly. The translation of technical manuals in the great libraries of the Islamic world or the Mongol Empire preserved engineering concepts that might have otherwise been lost, passing them forward to new generations. And often it was simple, direct observation. An engineer from one region could travel to another and simply study a functioning aqueduct or stepwell, learning its principles by seeing it in action, then adapting those principles to the unique challenges of his own homeland. This collaborative inheritance meant that each new empire did not have to start from scratch, rediscovering the wheel of hydraulic engineering. They could stand on the shoulders of hydrological giants, building upon centuries of accumulated trial and error. A Roman engineer in Spain could benefit from Persian groundwater knowledge without ever having seen a desert. A Chinese administrator could refine his flood control methods using mathematical concepts that had originated in Greece. This reveals a connected ancient world, far more integrated than we often assume, where the vital knowledge of how to move water was a universal language that flowed freely across all political and cultural borders, quenched by a shared thirst for survival and growth. The stone channels were more than just inert infrastructure. They were designed as living parts of the landscape. Ancient engineers demonstrated a profound ecological foresight, crafting their systems to work in concert with the natural world rather than dominate it. This began with a careful consideration of where to take the water from. When siting an intake structure on a river, they often chose locations that would draw only a portion of the flow, ensuring the main river channel remained strong enough to support the fish and other aquatic life downstream. They even designed specific features to protect this life. In some Chinese diversion weirs, you can find carefully carved openings that acted as early fish ladders, allowing migratory species to pass upstream and continue their vital reproductive cycles, undisturbed by the human-made structure. The materials they used were chosen with the water's purity in mind. They avoided stones or mortars that could leach harmful minerals or toxins into the supply, instinctively understanding that the health of the people was directly linked to the health of the water. This philosophy extended to the very process of cleaning the water. Those large, open sedimentation tanks at the start of an aqueduct were not just functional pits. As the water slowed, it would drop its silt, but this process also created new, calm water environments. These basins became accidental wetlands, providing habitats for frogs, water insects, and aquatic plants, which in turn helped to further purify the water through natural biological processes. The routes of their canals were planned with a similar sensitivity. Instead of cutting straight, sterile lines through the countryside, engineers would often curve their channels to follow natural contours, preserving existing trees and encouraging the growth of riparian vegetation along the banks. These green corridors did more than just look beautiful. Their roots knitted the soil together, preventing erosion and slumping that could have filled the canal with debris. They also provided essential shade, cooling the water and reducing evaporation, while offering shelter and passage for birds and land animals. Perhaps most remarkably, some systems were designed to give back. During seasonal floods, when water was abundant, certain canals and spillways were calibrated to deliberately overflow into designated infiltration basins. Here, the excess water would slowly percolate down through the soil, actively recharging the very groundwater aquifers that fed the mountain springs in the first place. This was a long-term investment in the water cycle itself. This entire approach was not born from a modern sense of environmentalism, but from a hard-won, practical wisdom gained over centuries. They understood that a river was not just a resource to be tapped, but a complex, living system. To disrupt it carelessly was to risk a cascade of consequences that could eventually undermine their own civilization. They knew that true sustainability required maintaining the health of the entire ecosystem, a lesson we are now struggling to relearn after generations of focusing only on extraction. High on the Bolivian Altiplano, where the air grows thin and frost is a nightly threat, the Tiahuanaku civilization performed a kind of agricultural alchemy. At a breathtaking 12,000 feet above sea level, their engineers faced a paradox: how to farm in a place where water could both drown their crops in the rainy season and vanish entirely in the dry months. Their brilliant solution was to reshape the very ground they stood on, creating a landscape of alternating ridges and canals known as raised field agriculture. They did not simply dig irrigation ditches. They sculpted the earth into wide, elevated planting beds, each one surrounded by a network of shallow waterways. This was not just about delivering water to plants, it was about creating an entirely new, self-regulating microclimate. The canals served as a giant thermal battery. Throughout the bright, high-altitude day, the dark water in these channels absorbed the intense solar radiation, storing heat with remarkable efficiency. Then, as the frigid night descended, this captured warmth would slowly radiate back into the surrounding air, creating a protective thermal blanket over the raised fields. This simple, elegant process could raise the ambient temperature around the crops by several critical degrees, just enough to shield tender seedlings from the killing frosts that would otherwise devastate them. But the canals did more than just provide heat. They were the heart of a complex hydrological cycle. During the heavy summer rains, excess water would drain directly from the raised fields into these surrounding channels, preventing the plant roots from becoming waterlogged and rotting. Then, during the long, dry winter, the process reversed. Through capillary action and careful management, the stored water in the canals would slowly seep back into the elevated beds, providing a consistent, life-giving moisture to the crops long after the rains had ceased. This system transformed the Tiahuanaku homeland into a veritable breadbasket. The constant nutrient flow from the canals, rich with decaying aquatic plants and sediment, fertilized the fields continuously, allowing for unprecedented crop yields. This agricultural abundance supported a dense urban population and a powerful state for centuries, all in an environment where modern farmers, with all their technology, still struggle with the climate's harsh limitations. The Tiahuanaku did not fight their extreme environment. They learned its rhythms and built a partnership with water itself, using its physical properties to carve a civilization out of the sky. This river of knowledge did not simply flow by chance. It was channeled through a rigorous system of education, a master-apprentice tradition that transformed bright youths into the engineers who could move mountains. A young person entering this path would begin not in a classroom but on a work site assigned to a master engineer. His first lessons were deceptively simple, learning to handle the sighting poles and water levels, understanding how to read the subtle tension in a knotted measuring cord. This was a world of practical mathematics, where geometry was not an abstract concept but the key to unlocking a river's path. He learned to calculate volumes of earth and stone, to project the necessary gradient for a canal over a mile of broken terrain, all under the watchful eye of his teacher. Mistakes were not punished as failures but seized as priceless learning opportunities, a chance to understand why a calculation had failed and how to correct it in the field. Before he was ever allowed to design a new channel, the apprentice would spend years on maintenance crews. He would descend into the dark, damp Qanat tunnels to clear silt, or help reset the stones of a terrace wall after a landslide. This hands-on work was the foundation of his education. It taught him to listen to the system, to recognize the faint signs of structural stress, the quiet gurgle that signaled a hidden leak, or the discoloration on stone that warned of internal erosion. He learned the properties of materials not from a scroll, but by mixing mortar with his own hands, feeling the precise consistency that would set correctly in the local climate. As his skills matured, his education expanded. Advanced students would study records of historical projects, analyzing the successes and, just as importantly, the failures of past masters. They became detectives of ancient engineering, learning why one aqueduct had stood for centuries while another collapsed after a few decades. They were even sent on journeys to neighboring regions or distant empires, traveling to examine a novel spillway design or a different approach to tunnel reinforcement. This cross-cultural study broadened their perspective, allowing them to bring home innovative solutions and adapt them to local challenges. This educational model was a perfect engine for progress. It ensured that the hard-won wisdom of one generation was not lost to the next, while simultaneously encouraging innovation. Each new engineer stood upon the shoulders of giants, equipped with centuries of accumulated knowledge, yet empowered to find new answers for an ever-changing world. The proof of its effectiveness is written in stone, in the aqueducts and canals that functioned for 1,000 years, outliving the very empires that built them. But a single river could power an entire city. In the heart of ancient Persia, the Karun River, the nation's most powerful waterway, presented both a promise and a threat. Its tremendous flow could either fuel an empire or flood it into oblivion. The engineers of the Shushtar historical hydraulic system did not choose one or the other. They chose to harness it all, creating a multi-layered masterpiece that turned a river into a complete working city. Their first act was one of breathtaking audacity. They did not merely divert the Karun, they tamed its main channel with a massive weir, a foundational dam that forced the water to make a choice. A portion continued down the original riverbed, but the rest was funneled into a new, man-made course, a diversion canal that acted as the system's main artery. This was the crucial first step in a grand design, controlling the very heart of the river before it even reached the city. From this main canal, the true complexity unfolded. The engineers carved a series of tunnels directly through the living rock of the mountain cliff. These were not simple channels. but precisely graded conduits that guided the water downward, using gravity to build up speed and power. As the water burst from the mouths of these tunnels, it was not released into a calm pool. Instead, it was sent cascading down a series of dramatic, artificial waterfalls, a thundering spectacle of raw energy. But this was not for show. At the base of these falls, the engineers had constructed an entire industrial complex. The relentless, pounding force of the falling water was captured to drive the wheels of more than 40 watermills. These mills, built into the cliffside, formed the city's industrial engine, grinding grain for flour with an efficiency that could feed a vast population. This was hydropower on a scale the ancient world had rarely seen, turning the river's destructive potential into productive, mechanical force. Yet the system's genius was its refusal to waste anything. After the water had spent its energy turning the mill wheels, it did not simply drain away. It was carefully collected and channeled into a second, lower network of canals. This reclaimed water was then distributed across a vast, sun-scorched plain, transforming barren land into thousands of acres of fertile orchards and farmland. The entire process was a closed loop of perfect utility. The same volume of water first powered industry, then sustained agriculture. The system even included precise flow control mechanisms, a series of adjustable gates and weirs that allowed water masters to manage the distribution based on the season. During planting time, more water could be directed to the fields. During the dry industrial season, the flow could be maximized for the mills. This was holistic thinking made real in stone. The Shushtar system was not just an irrigation project or a power plant. It was a single, integrated organism that addressed urban, industrial, and agricultural needs simultaneously. A symphony of water where every drop played multiple roles before returning to the earth. Even the grandest projects sometimes failed, and it was in these dramatic collapses that ancient engineers found their most profound teachers. A tunnel carved through unstable shale might cave in after a single season, burying years of work and sometimes the workers themselves. A dam perfectly designed on parchment could be torn apart by a flood it was never meant to withstand. These were not just disasters, they were brutal but essential field tests, revealing the hidden weaknesses in their understanding of the land. Each failure forced a fundamental question: why did this rock give way? Why did that foundation wash out? The answers were not found in libraries but in the wreckage. A collapsed tunnel taught engineers to recognize different types of rock strata and how they reacted to the constant pressure of water and earth. They learned that a straight channel through a mountain's weakest layer was an invitation for disaster. This hard-won knowledge led to the development of sophisticated support structures. They began constructing arched brick linings for their tunnels, a shape that distributed the immense overhead pressure down and out into the surrounding bedrock, creating a much more stable passage. They also learned to curve their tunnels slightly, avoiding the most treacherous fault lines and following the natural grain of the mountain's strength. Similarly, a breached dam was a masterclass in hydrology. A wall that stood firm against normal flows could shatter when a once-in-a-century storm sent a mountain of water crashing into it. Engineers realized that a dam was not just a wall, it was part of a system. They began designing auxiliary spillways, secondary channels positioned well away from the main structure. These acted as pressure relief valves, automatically diverting catastrophic floodwaters around the dam and into a safe floodplain, saving the primary structure from destruction. They also became obsessed with the invisible ground beneath their foundations. A breach often revealed that water had been seeping underneath the dam, slowly eroding the soil and creating a hollow space. In response, they developed deep cut-off walls, driving rows of timber or stone pilings deep into the riverbed to create a subterranean barrier that blocked this undermining flow. Sedimentation was a quieter, more insidious enemy. A canal that ran perfectly for a decade might slowly choke to death on its own success, as silt carried from the mountains gradually filled its channel, reducing the flow to a trickle. This persistent problem sparked a revolution in water treatment. Engineers began constructing elaborate settling basins at the very head of their canal systems. These were wide, shallow pools where the water's flow was deliberately slowed almost to a standstill. Here, the heavy silt and sand would fall out of suspension and settle to the bottom, allowing much cleaner water to continue into the main channel. To enhance this, they sometimes added filtration layers of gravel and sand, creating a passive but effective cleaning process that protected the entire network from gradual clogging. Crucially, these lessons were not lost. Master engineers meticulously documented what went wrong, creating scrolls and tablets that served as cautionary tales for the next generation. A new apprentice would study the records of a dam failure in a distant province, learning about foundation preparation without ever having to witness the destruction himself. This created an iterative cycle of progress, a slow accumulation of wisdom where each failure refined the rules for the next project. It was this humility in the face of nature's power, this willingness to learn from catastrophe, that gave them the confidence to eventually redirect entire rivers and move mountains, not with blind arrogance, but with the hard-earned certainty of those who had already seen what could go wrong. A river's flow is meaningless without a system to ensure its gifts reach everyone. These ancient engineers understood that their stone channels and spiral wells were only half the solution. The other, equally vital half was a framework of laws and administration so precise it could measure a day's worth of water for a single farmer's field. In the shadow of their aqueducts, societies developed the world's first water courts, where disputes were settled not with force, but with meticulously kept ledgers and inherited custom. The fundamental principle was simple yet profound. Water did not belong to the individual, but to the community, and its allocation was a sacred trust. This belief was codified into detailed legal systems that specified exactly how much water a person could draw, often down to the minute. Your right was not based on wealth or power, but on practical, transparent factors. The size of your land, the type of crops you grew, and crucially, your historical usage all determined your share. A farmer growing thirsty date palms would receive a larger, longer allocation than his neighbor cultivating hardy barley. This was not arbitrary. It was a calculated distribution of a life-giving resource to maximize the entire region's agricultural output and ensure no one was left without. But how do you stop an upstream landowner from simply taking all the water for himself? The answer was a strictly enforced rotational schedule, a celestial clockwork of water rights. Canals were divided into sections, and each section had its designated day and time for access. A watermaster, a public official vested with immense authority, would travel the network, opening and closing sluice gates according to this unchangeable calendar. If it was your turn for the night irrigation shift, you would be there with your lantern, ready to channel the precious flow onto your land, knowing that at dawn the gate would close and the water would move onto your neighbor's plot. This rigid timetable prevented hoarding and ensured that the community at the very end of the canal, sometimes dozens of miles from the source, received their fair share. Enforcement was the domain of special water magistrates, judges who possessed an almost priestly knowledge of the local hydraulic laws. Their courts would hear cases between farmers, between villages, and even between entire regions. The evidence was often the system itself, They used standardized measurement devices like calibrated stone weirs or precisely notched wooden gauges set into the canal walls. These tools provided an undeniable, objective measure of flow, turning a subjective argument into a simple matter of reading the water level against a mark. A magistrate could look at a notch and declare, "You have taken 2 finger widths more than your right," and the fine or correction would be immediate. This entire administrative machine, from the legal codes to the water masters, was not merely about efficiency. It was the primary defense against the chaos of scarcity. In a world where a stolen hour of water could mean a failed harvest, this transparent, predictable system maintained a fragile peace. It demonstrated that the most brilliant engineering could still fail if it was not paired with a governance structure the people perceived as just. The true monument was not just the aqueduct, but the trust it carried. Deep in the deserts of Western China, the Karez system transforms the very meaning of survival. Beneath the scorching expanse of the Turpan Depression, one of the hottest and driest places on the planet, lies a hidden river network stretching over 5,000 kilometers. This underground labyrinth taps into a secret bounty, the groundwater flowing from the snow-capped Tiahuanaku Mountains, channeling it beneath the blistering flaming mountains and across the sands to create pockets of life. The Karez is a masterpiece of communal effort, a project so vast it could only be built over generations, with each new tunnel extending the reach of civilization further into the void. Its construction was a symphony of precision and peril. Teams of diggers began by sinking a mother well deep into the foothills, plunging straight down until they struck the life-giving water table. From this starting point, they began their subterranean march. At regular intervals, sometimes as close as every 30 meters, they dug vertical shafts straight down from the desert floor. These shafts were not the goal, they were merely access points and lifelines. From the bottom of each shaft, crews would dig horizontally in both directions, painstakingly connecting the shafts with a gently sloping underground canal. The true challenge was maintaining that perfect, gravity-fed slope across kilometers of unseen earth. How could they possibly ensure the tunnel was angled correctly when they were working in near-total darkness, guided only by oil lamps and simple sighting tools? They used the vertical shafts themselves as guides, lowering calibrated plumb lines to check their depth and alignment, ensuring the water would flow with just enough force to move, but not so fast that it would erode the delicate tunnel walls. The ventilation design was another stroke of genius. The regular vertical shafts created a natural stack effect. As the hot desert air at the surface warmed the shafts, it would rise, pulling the stale, humid air from the tunnels upward and drawing fresh air down through other shafts. This passive ventilation system was crucial for the workers toiling below, preventing the buildup of toxic gases and providing just enough oxygen to keep their lamps burning and their lungs clear. It also served a second, equally vital purpose. By keeping the water flowing in a cool, dark, underground channel, the Karez system almost completely eliminated the devastating evaporation that would have claimed any open canal in the desert sun. At the end of its long journey, the water did not simply spill out onto the sand. It was carefully managed through a series of storage reservoirs and settling basins. These open pools, often located at the edge of an oasis, allowed the water to be stored during times of low demand, such as the cool night, and released during the heat of the day when crops needed it most. The entire system was a lesson in balance, a slow, deliberate rhythm that matched the patient pulse of the desert itself. For over 2,000 years, the Karez has sustained communities in a place where life should be impossible, proving that the deepest wisdom often lies not in conquering a landscape, but in learning to listen to its hidden currents. The silent wisdom of those ancient channels still whispers to us today. modern engineers grappling with unprecedented water crises are increasingly turning to the past for solutions. They discover that these forgotten systems were not just historical curiosities, but sophisticated models of sustainable design. In arid regions from the American Southwest to the Middle East, the principles of the Qanat are being revived. Instead of pumping groundwater to exhaustion with powerful electric wells, new projects encourage the slow, natural recharge of aquifers, mimicking the gentle, gravity-fed flow of the ancient Persian tunnels. This shift in thinking prioritizes the long-term health of the water table over short-term extraction, a lesson in patience we are only now relearning. On the unstable hillsides of Southeast Asia and South America, the ghost of the Inca terraces is visible in modern slope stabilization projects. The same logic of turning a steep, erosion-prone slope into a series of level, reinforced steps is used to prevent catastrophic landslides and reclaim degraded land for agriculture. This ancient technique proves more resilient and ecologically harmonious than many modern concrete retaining walls. The most profound influence, however, may be the holistic vision of systems like Shushtar. Today's most advanced water management plans no longer treat drinking water, agricultural irrigation, and hydropower as separate problems. They are designed as interconnected systems where water is used and reused in a cascading sequence, just as the Karez River first powered mills and then nourished orchards. This integrated approach maximizes every drop in a world where every drop counts. Perhaps most humbling is the moment when supercomputers and fluid dynamics models confirm what an ancient engineer knew in his bones. When digital simulations map the flow through a 2,000-year-old canal, they often find its dimensions and slope are nearly perfect for minimizing silt buildup and maximizing efficient delivery. Their empirical solutions, born from generations of observation, consistently align with our most advanced hydraulic equations. This enduring relevance reveals a profound truth. Those lost engineers were not just moving water, they were deciphering a fundamental language, the inherent behavior of water itself. Their genius lay in listening to that language and designing in harmony with its rules, a form of wisdom that no amount of technological advancement can ever make obsolete. The silent wisdom of those ancient channels still whispers to us today. Modern engineers grappling with unprecedented water crises are increasingly turning to the past for solutions. They discover that these forgotten systems were not just historical curiosities, but sophisticated models of sustainable design. In arid regions from the American Southwest to the Middle East, the principles of the Qanat are being revived. Instead of pumping groundwater to exhaustion with powerful electric wells, new projects encourage the slow, natural recharge of aquifers, mimicking the gentle, gravity-fed flow of the ancient Persian tunnels. This shift in thinking prioritizes the long-term health of the water table over short-term extraction, a lesson in patience we are only now relearning. On the unstable hillsides of Southeast Asia and South America, the ghost of the Inca terraces is visible in modern slope stabilization projects. The same logic of turning a steep, erosion-prone slope into a series of level, reinforced steps is used to prevent catastrophic landslides and reclaim degraded land for agriculture. This ancient technique proves more resilient and ecologically harmonious than many modern concrete retaining walls. The most profound influence, however, may be the holistic vision of systems like Shushtar. Today's most advanced water management plans no longer treat drinking water, agricultural irrigation, and hydropower as separate problems. They are designed as interconnected systems where water is used and reused in a cascading sequence, just as the Karez River first powered mills and then nourished orchards. This integrated approach maximizes every drop in a world where every drop counts. Perhaps most humbling is the moment when supercomputers and fluid dynamics models confirm what an ancient engineer knew in his bones. When digital simulations map the flow through a 2,000-year-old canal, they often find its dimensions and slope are nearly perfect for minimizing silt buildup and maximizing efficient delivery. Their empirical solutions, born from generations of observation, consistently align with our most advanced hydraulic equations. This enduring relevance reveals a profound truth. Those lost engineers were not just moving water, they were deciphering a fundamental language, the inherent behavior of water itself. Their genius lay in listening to that language and designing in harmony with its rules, a form of wisdom that no amount of technological advancement can ever make obsolete. These echoes from the past are not just history, they are a blueprint for the future, and their story continues with you. The genius of these ancient engineers was their ability to see the big picture, to understand that water connects every part of our world. That same perspective is needed now more than ever. We would love to hear your thoughts in the comments below. Which of these engineering marvels most captivated your imagination? Was it the silent, spiraling Puquios of the Nazca, the self-regulating magic of Dujiangyan, or the sheer audacity of the Roman aqueducts? And more importantly, which of these forgotten techniques do you believe could be adapted to solve the water challenges we face in our own communities today? If exploring these lost chapters of human ingenuity has sparked your curiosity, consider subscribing to the channel. We are constantly unearthing more stories of history's greatest technological achievements, from forgotten machines to architectural wonders. Be sure to hit the notification bell so you can join us for our next deep dive into the past's most fascinating mysteries. Your engagement, your questions, and your shared wonder are what fuel this journey of discovery, helping us all to piece together the incredible legacy of those who came before us.